Hello and welcome to this manufacturing process technology part 2 module 47. We were talking and discussing about the rolling process, and we actually tried to figure out what is a neutral angle in the last step, where we equated the P by 2K value before and after, and in this manner were able to find out a common lambda n through which you could actually find out what is going to be the neutral angle theta n for the rolling process. So having said that, if we wanted to plot the P by 2K, that is the the pressure ratio, you can say, with respect to the yield criteria, and that you plot with respect to theta, you are basically, so this is the exit side of the roll maybe, and this is the entry side. So we are left with a plot something like this, where the maximum value of this would happen to be at lambda equal to lambda n, okay, and theta equal to theta n. So this is the neutral point actually. So the P by 2K value really would peak around the neutral point, where you can say that the before and after the neutral point, whatever P by 2K values are, sort of equated at the neutral point, so that there is a continuity of the pressure related to this value. So this hill right here is also known as the friction hill, which is very commonly used terminology in case of rolling processes, which corresponds to an angle theta equal to theta n, neutral angle, which has been calculated earlier by this expression before. So let us now determine the other parameters related to the rolling process. One of them is the roll separating forces. And for doing this, we again assume in a similar manner the width of the strip to be unity. So width of the strip that is being rolled is taken as unity, and the total force F trying to separate the rolls that comes here can really be obtained. So let us say F is the total force trying to separate the rolls. So F is basically equal to 0 to the value theta I, the whole angle that basically the roll covers over the sheet at point equal to 0, okay, of the total force here, which is actually equal to the if you assume the width to be unity, the pressure which is there from the roll times of r cos theta. If you look at the way, again let us go back, so if you look at basically this earlier figure right here, that this is the direction of the roll pressure P, and it is at an angle theta with respect to the horizontal. So we are talking about the separating roll force, which is a component of this P, which actually is imparted by the sheet onto the roll, so that the rolls try to separate out because of the rolling process, okay, and they are held in place by their bearings. So it's actually some kind of a bearing load that we are talking about. So this is P cos of theta times of the area of this particular sheet, which is actually nothing but the total radius of the roll times of d theta. So this r d theta is the length of this particular element that we are talking about, times 1, which is the width of this particular element, gives the area. So pressure times of r d theta is the total amount of force, and the component of this force in this direction is F cos theta, okay. So that is how you consider this particular expression, and that is how you generate this roll force, as I was illustrating here in this example, as PR cos theta d of theta. So having said that, now if you have this as the vertical force which is trying to separate the rolls because of the insertion of the sheet metal and if we again assume the theta value to be small, so since theta is small, we can have the cos sort of converge to 1, cos of theta converge to 1, and we are left with approximately an expression 0 to theta I of pressure P times of r d theta to be equal to this force F. But mind you, there is a problem or a catch here, and the problem is that you know, if we are talking about the whole angle 0 to theta I, this really needs to be divided into two different angles, 0 to theta n, which is the neutral angle where the friction force is assumed to be enabler for the rolling process to happen, and after the neutral angle the friction force becomes a disabler. Okay. So we have 0 to theta n p, let us say, after, because this is really the point, you know, if you look at the way that theta was assumed, the theta was assumed from the neutral point onwards. So this basically is again illustrating the whole rolling process, and as you see here, the angle theta actually starts from this last point of contact all the way to this particular point here, and theta I in fact is from theta equal to 0 at this end all the way to theta I. Okay. So theta towards the initial initial sort of point of contact of the roll with respect to the work surface. So when we are talking about neutral point really, so there are two issues. One is from theta equal to 0 to theta neutral point where the friction force is playing the role of a disabler, and beyond the neutral point all the way to theta I where the friction force is playing role as an enabler. So having said that, now let us look at this equation. We can modify this as 0 to theta n p after times of r d theta plus integral of theta n to theta I. Okay. And then you have p before, which is actually an enabler in this case, times of r d theta. So that is how you have the total force or obtain the total force of the rolls because of the whole forming process. So normally the integration of this is this equation is a computational affair. So integration of this equation is normally computed numerically, and therefore numerically it gives quite a good reasonable estimate of the total force faced by the rolls. So the other issue is of course the driving torque and the power. So let us look at that part as well, the driving force or the driving torque and the power that is needed for the rolling operation. Obviously we intuitively can think of that the driving force or the driving torque in this particular case is required to overcome the torque exerted on the rolls, torque exerted on the roll by the interfacial friction force, and you can say the friction force to be mu p. Okay. So therefore the total torque can be represented as probably 0 to theta I times of this whole mu p times of the r d theta, which is actually equal to the width of that element, one its unit width in the z direction. So you have r theta times of 1, r d theta times of 1 times of, because it is a torque and the torque is really played because of frictional force which is tangential to the roll surface at the center of the roll. So you multiply that with the torque radius r in this particular case, and we can easily, because you know this p value would change its properties before and after the neutral point. So again we are left with estimating this with minus of 0 to theta n, because this actually is a disabler, mu p after times of r squared d theta plus again theta n to theta I when the friction force becomes an enabler. So this is positive torque mu p before r square d theta. So it should be noted that the friction would resist after the neutral point the rolling action, and before the neutral point it will enable or aid the rolling action. So because of using this method, the result would really come as a difference of two very large quantities, and there will be a lot of numerical error, if I wanted to numerically calculate these two integrals, they are going to be very large quantities, and there is going to be a significant numerical error in this method. So calculating torque, although it is logically correct, but calculating torque in this manner may have involves the computed values of the integrals 1 and 2 mentioned above. This is integral 1, okay. Let us just write this as integral 1 and this is integral 2. So involves the computed values of integrals 1 and 2, and therefore because both of them are sort of cancelling each other, there is going to be a large error. So, okay, so which are quite large. The numerical error will also be very large. So let us look at some kind of an alternate strategy by not really directly calculating what is going to happen by the friction on the rolls, but to sort of consider the horizontal equilibrium of the deformation zone of the strip to calculate the torque with probably more accuracy than such a large numerical error which is involved in the last step here. So in this case we would like to determine T by considering the horizontal equilibrium of the deformation zone and this is shown right here. So you have now many forces which come into play. This is, let us say, the whole volume of the strip, where on one side the thickness changes to some T final value, and on the other side it starts gets pressing into the roll at thickness T initial, and you are having torques on both sides. One of them is sigma xi, another is sigma xf, okay, and similarly you also have roll pressures all along the way. So the pressure of the rolls are actually perpendicular at every level, corresponding to the curvature of the sheets which are being pressed, and so it will result in some kind of equivalent horizontal force Fe, which can be represented by a cross section of this dotted line with respect to the profile here on both the sides. And so this Fe value is the one which is created by the friction between the roll and the sheet, and it's able to push forward the sheet from between the gaps in the roll, okay. So having said that, the equivalent horizontal force Fe represents the net frictional interaction between each roll and the strip. So therefore the reaction minus Fe of this force Fe has to be overcome by the roll driving torque T. So that is the consideration in this case, and therefore calculating Fe is much of a simpler job than calculating the numerical value of this integral and trying to create the net torque out of it. So let us actually see in this particular force system here, right here, how to calculate this Fe. So the force Fe can really be determined by looking into the, let us say, the net force in the direction from initial to final, which is actually given by half times of, remember the section has a unit width coming out of the plane of the paper here or plane of the screen here. So here half sigma xi times of Ti minus of sigma xf times of Tf is going to really give the total forces on this element because of the torque. And you have to remember why this half factor here is because when we are talking about this particular element, all we mean by the coordinate frame is to look at the thickness, which is actually y is basically Tf by 2, and similarly it is Ti by 2 on both sides. So we are following the same coordinates here. So that is one, and then you have a frictional force here, and the frictional force here again will be given by again twice 0 to theta I, the roll pressure P times of R sine of theta times of d theta. Obviously the width is unity, so R d theta times of unity is the area, and you can think of it that the pressure P, which is actually at a certain angle here, let us say if this is the pressure P at a certain angle theta here. So we are talking about a component of this P which is trying to sort of push the sheet out from the smaller thickness to the higher thickness side. Okay, so in this case the component of the roll pressure is really not aiding the rolling process. So it is only this Fe force which is responsible for the net force towards the right. Okay, so these forces are towards the right here, which would cause the sheet to move forward, and therefore it has to essentially overcome the difference between the stress area product of the left and the right, and also the component of the roll pressure on the surface of this particular element that we are talking about, which is R d theta. Okay, so you can probably at smaller thetas estimate this to be approximately half times of sigma xi Ti minus sigma xf Tf plus so basically I'm sorry, I just made a small error here. This is only about one side of this force Fe, because we are talking about only the upper half here. Just look at it in this manner, that we are talking about y equal to Ti by 2 or Tf by 2. So the amount of roll pressure and the component of the roll pressure is only because of one of the rolls on the top side, and therefore this is actually 1 into and not 2 into. Okay, so we just modify this here by writing plus 0 to theta I times of P times of R, and you have we can mention, or we can substitute approximately sin theta as theta because of smaller theta. So we are actually sort of assuming here smaller values of theta. So we have P R theta times of d theta as the final formulation, and obviously if this is the total amount of frictional force, the torque that this force will exert on the center of the roll would actually be the Fe R product, or force times radius product, or force radius product, and this torque is approximately estimated as half R times of again sigma xi times of Ti minus of sigma xf times of Tf, so obvious reasons, plus integral of 0 to theta I P R square theta d theta. And you have to remember then again that when we are talking about the roll, we have to sort of divide this into again two parts. One is 0 to theta n P R square theta d theta plus theta n to theta I, and this is for P after, and this is P before. Okay, P before R square theta d theta. So that's how you calculate actually the torque value, rather than creating a direct role of friction here, you basically try to find out what is the force that is needed for pushing the element, and that is assumed to be, if there are no other losses which are there of the energy, then it is assumed to be the same as the force that is needed for pushing the element forward, or the force on the roll, friction force on the roll. So there is no loss between these two forces, and they are equal and opposite to each other. So therefore that is an alternate strategy to calculate what is going to be the torque value. So power, as you know, in this particular case is given by torque omega. So if I had a certain value of torque and if I knew that the rolls are rotating at a certain omega, a certain RPM, we should be able to give a good estimate of what is going to be the rolling power. So we have now made a case where we have tried to mechanistically observe the rolling process very closely. We have tried to make a force balance through which we could predict what is going to be the roll pressure, what is going to be the frictional force, what is also going to be the driving torque, and the power which is needed for driving the roll, okay, or executing the rolling process, and then also try to determine what is going to be the roll separating force. So typically all the different forming examples, be it forging of a block or forging of a circular disc, or maybe even the extrusion, or drawing or deep drawing or bending processes, they have to be modeled sort of in that manner, so that you can have sort of a mechanistic first principle based modeling of the various factors, like what is the power that is needed to execute the process, or what are the kind of forces that are subjected or that are being subjected onto the material by the either the roll or the die in case of forging, so on and so forth. So I am not going to go into the modeling of any other aspect at this time, because we are already at towards the end of our lecture. But what I am going to do is to sort of give you some brief sort of schematic illustrations about the various metal forming processes which are there, and then maybe talk a little bit about additive manufacturing and close this topic of manufacturing process technology part 2. However, we have made sure that there are online notes available for the different processes, like forging of a block, or forging of, let's say, a circular block or a rectangular block, or even related to extrusion. So if you have any kind of queries or questions, the modeling is typically made in the same manner as has been given here mechanistically. So you can actually feel free to interact through the online portal, and we'll try to answer all your queries or take up all your queries. So let us now look into the different processes which are available. So we have already done the rolling process. So rolling can be done in various configurations of rolling mills. You can have a 2 high rolling mill, as has been seen here, a 3 high, where again, as you can see that there are a set of 3 rolls spaced by different distances. So you have the first pass somewhere here, and the second pass where the metal is sort of refed back, okay, from the first gap into the second gap right here. We also have again rolling done with different orientations, like 4 high rolls, or cluster rolls, or cluster mills, or tandem rolling mill. So typically the role of the 4 high or the cluster mills is to provide the support or the added support which is needed for rolling of hard materials particularly. So you provide a backup support for the main roll, which is creating the actual deformation process of harder material. You have 2 different configurations for that. One is the 4 high, or another is the cluster mill configuration that you can see, and in tandem means that you are having a successive reducing pass as you are going between different rolls at certain feed velocity, so that you can have a thinner section emerge from a thicker section by just in tandem or rolling sequentially between different roll gaps or roll separations. So that's about rolling. We have other processes of significance, like forging, where you either can have a open die forging case, and there is a very nice illustration in the notes as well, where we talk about how frictional force related to the die here and the expanding metal would vary. And there would really be a point where the deformation would be at the same velocity as the or the force of deformation, or the stress, total principal stress would be the same value as the frictional force, okay, between the dies and the workpiece. Similarly, you have again impression die forging, where there is, so where you have some kind of an impression or a cavity being created in the die, and basically the shape gets formed because of the the negative shape gets formed on the metal element because of the cavity which is shaped into the forging die. There are other processes, particularly extrusion. It's a bulk deformation process in which the work is forced to flow through a die opening. You can produce desired cross sectional shapes. There are different kind of extrusions, for example direct extrusion here or indirect. As you are seeing here in this direct extrusion case, there is a direct forming being incorporated by pressing a billet, a work billet from a small orifice which is available in this particular die to generate the final work shape. You can do a solid shape or a hollow shape based on if there is a there is an additional mandrel to create this hollow. Similarly, in an indirect extrusion process, as you can see here, you are basically trying to flow the metal in the reverse direction through the gaps or the the sort of in this case it is for the gap formulated by a solid cross section, or if there is a hollow cross section also a similar kind of backflow of the metal can happen because of the ramming action done in a direction from left to right. So this is again in an indirect manner you are doing the same metal forming process like what was happening earlier by just direct hitting of a work billet. We also have various other sheet metal working processes like bending, where there is a punch which is used to basically bend thin sheets. Okay, you can also draw thin sheets as is illustrated here. There is a die cavity, and the punch and die cavity in unison is able to create a sort of a drawn shape of the cavity. There is also a shearing action which happens in two states, where one there is a punch which comes and strikes on the workpiece here, and then there is a cleaving off which happens at this particular interface, and that is the second part of the process after cutting, where the remaining part of the sheared component of the sheared sheet is taken away from the zone of shearing. So that's how some of these operations are schematically shown. The idea here is why we are discussing this is that in the same manner as we did rolling, you have mechanistic models available for each of these processes, and this kind of concludes from our side the whole metal forming domain. We also wanted to do a small module, an introductory module to additive manufacturing, for which I'll just have a few slides as a ending for this manufacturing process technology part 2. So let's look into additive manufacturing. So you have various conceptually different techniques of manufacturing. One is subtractive manufacturing, where really it is about starting from a bigger shape or a size and then trying to chip off this so that there is a material removal, and because of the material removal you obtain this shape of the final product, and that's typically called subtractive manufacturing, because you are taking off material from the billet in order to convert it into a hollow cavity shape like this, which has been indicated here in the final product. However, in the additive manufacturing it is actually just building upon rather than subtracting. So you have a small base rolled sheet which is to be built upon, and for building up you are using a wire, and you are trying to melt the wire and deposit it locally on the top of this rolled sheet, so that from this initial shape you can have a final product. So here there is really no chipping action or subtractive process, but an additive build up, and the build up is done by a wire which is typically heated and fed, and whatever shapes and sizes need to be realized, the spooler of this wire which actually feeds the wire and extrudes the wire kind of moves, okay, and creates this section by section deposition so that you can have the final product. So this is really the basic difference between what you had done earlier in machining and what you would be doing now in additive manufacturing. There are many different kinds of additive manufacturing processes. For example, you have the very famous FDM or fusion deposition modeling, which actually I illustrated also, and there is a video on lecture 48 which has been recently uploaded for seeing that how from a soft drawing you could convert using the FDM process into a complex part. There are other processes like stereolithography, then this digital light projector based 3D printing, again photopolymer phase change, inkjets, polyjets kind of additive manufacturing. You have selective laser sintering, which is a process which is used not only for polymers but also for other classes of materials like metals. You have direct metal laser sintering as well. Then you have many others like plaster based 3D printing or thermal phase changed inkjets, or then laminated object manufacturing, etc. So we are going to look into few processes here which will give you some basic idea about these additive manufacturing processes. So let us now first understand what is the fusion deposition modeling. So this process was developed in the 80s by Scott and Lisa Crump, and it is basically trademarked by a company called Stratasys, which actually provides this technology. This technology is based on various events which happen across this drawing. Here you can see there is a filament of a plastic wire which is normally being pushed into a heating block here, and this heating block is something like an extruder which actually melts the material into a sort of a oozing out jelly, okay, and this only happens when the metal goes into its, so the material to its glass transition temperature, through which it comes into a usable flow state. And then what happens is that you can often move the bed in the x and y axis and the extruder in the z axis, so that you have a layer by layer deposition. And so the interface that this machine has is really through a very powerful CAD package which kind of takes any shape and cuts it into various sections, and one section is actually equal to the thickness that is being deposited at one run or one particular layering as given by this device. So it is really dependent on the resolution of the whole system as to how this z axis movement can be realized from one step to the other. So this right here shows an extruder assembly by makerbot.com, and there are different components in the FDM system like a CNC table, a stepper motor, a controller, a material filament, an extruder assembly, and a hotbed, which is typically used for realizing any such fusion deposition modeling. In fact, we have a detailed video that I have given for this using a machine called FDM Titan, again manufactured by Stratasys and sold by Stratasys. So please have a look at it. It's actually your lecture 48 or module 48 on this particular course set. The other very interesting method that is available for additive manufacturing is this SLA, the stereolithography method, where the idea is that again now you have a resist, okay, it's a photosensitive polymer, and when you heat cure, or when you basically try to cure this polymer with a laser beam in a section by section manner, you can actually have the resin to flow back and forth between a moving plate, okay, and the sectional thickness that has already been incorporated and exposed at different heights or different depths, so that the whole structure can be built up. I think I had given a detailed illustration of stereolithography while looking at the microsystems fabrication processes. It is basically process wise exactly the same. The only thing is that there is a utilization of a laser here, and it is basically again a motion of a XY scanning mirror which would try to write down the different sections, okay, across the SLA. So the UV light or a UV laser is basically cross linking the monomer on the thin liquid film above the structure and support base, and the elevator plate is lowered by a small prescribed step, exposing a fresh layer of the liquid monomer, and the process is repeated like this, and at the end of the job the whole part is cured once more after excess resin and the support structures are removed from it. So that is how you do a layer by layer printing. So the various factors affecting the stereolithography process, in fact we can estimate the time that is needed to complete one layer I. Basically there may be n such layers which are there in a system. So we can actually estimate the time required to build the part by this layering process from about 1 hour for small parts, simple geometry, to up to several dozens of hours for complex parts, okay. And so the other factors that would affect really are the cycle time, the cycle time or the scan speed, and also the layer thickness that is incorporated. So in general there is a sort of a very simplistic way of estimation of the time. So the total time that is needed to complete a layer I in seconds can be given by the area that you are trying to print of this layer I, okay, in mm square, divided by the velocity diameter product of the scanning laser beam. So if V is the average scanning speed of the laser beam at, let us say, millimeters per second, and D is the diameter of the laser at a surface spot. So basically if you have a spot and let us say there is an area like this where this spot has occurred and there is a center of the spot which is moving at a velocity V. So the area that this spot would basically cover, okay, is by its motion per unit time is going to be really dV, okay. And so that is exactly what we are trying to say here, that if AI, the total area, is divided by this dV, the diameter velocity product, you are going to get an idea of how much time the scanner is going to take to scan the whole area AI. And added to this is the time for repositioning which happens between the layers, because obviously between one layer and another there is some kind of a transition time before the the scanner can move back to the portion to the origin from where it started this whole scanning activity. And this origin could be either side, wherever it has completed its last step, or if you want to set it back, it comes back to the machine 0. So depending on what is going to be the strategy that you are using, you can vary the time in this manner, and so that is going to be equal to the time required for the ith layer. And if you had exactly n1 layers, I can say the total cycle time in this particular case, build cycle time, is basically represented as the summation of all such TIs between I varying between 1 and n1, where n1 are the number of layers which are being used. So there is a small example problem here which looks at it. A prototype of a tube with a square cross section is fabricated using this SLA technique. Outside dimensions of the square are given to be 100 mm and inside dimensions are about 90 mm, and wall thickness almost everywhere is about 5 mm except at the corners where it is slightly higher, and the height of the Z tube in the Z direction, the height of the tube is about 80 mm, and the layer thickness that we are using here is 0.1 mm. So obviously if you are having 80 mm and 0.10 mm as one layer thickness, so there are about 800 layers that you are trying to obtain, okay, and each layer should have a time which is based on obviously the spot size, the diameter, and of course the total area. In this case the area of cross section, because it is a hollow tube of square cross section that we are creating, we have the area as 100 square minus 90 square, which is about 1900 millimeters square. So that is AI, okay. And so with this AI, if I wanted to find out what is going to be the total time for one layer, you are just going to divide this with the laser beam diameter times the mm per second of the scanning speed of the laser beam. So this comes out to be equal to, so the TI basically comes out to be equal to this plus the repositioning time TR, which is about 10 seconds in this case. It's just saying that 10 seconds are lost in each layer to lower the height of the platform and hold the part and maybe just take things back to the origin. So here therefore the TI comes out to be 15.2 plus 10, that is 25.2 seconds, okay. AI being equal to 1900 millimeters square, and therefore the total number of layers that you are manufacturing is 800. The cycle time required is about 336 minutes, which is 5.6 hours. So that is how you estimate, in a preliminary manner, what is going to be the time for the total cycle, okay, to happen. You can see this part has been manufactured in a relatively higher time of about 5.6 hours. That is because the extremely slow nature of the SLS system. You have again the selective laser sintering, which is normally used by having this powder delivery come fabrication post. There is one piston here which shows the feeding of the powder, which is actually a sort of you can say a powder which is fused together to create the whole part, okay. And then also the feeding of this powder using a roller assembly into this other piston which moves in steps downwards, and each time it moves after the scanner system using a laser has scanned and sintered a portion. So this is actually fabricated part by sintering as a result of the downward motion of the piston here. So that is how the SLS systems work. The advantage this system has is that it not only does polymers but also is able to do on metals, and after removal of the machine from the machine, the unsintered dry powder is brushed off and recycled so that you can have the part without the powder. So materials that you can use typically vary between glass, polymers, nylon, polystyrene, metals, particularly steel, titanium alloys, ceramics, so on and so forth. It does not require any support structure or overhangs. They are typically supported by powder material. All you need to do is to sort of retain the powder without putting the laser into that region, and then this powder can be again reused back into the system. So that is how SLS is done. There are some parts here manufactured by the simple SLS process. Obviously it is expensive relative to the fuse deposition modeling or even the 3D printing done earlier by the other step like stereolithography, but also there is another limitation that the quality of the metal parts that you produce are really not as high as e-beam machining would produce, and in this case you may not serve the strength requirements that is needed by some of the dynamic machinery to produce such metal parts. So then there is this digital light projector based 3D printing, which I had already illustrated earlier, that instead of a single laser point scanning the whole structure, in this particular case it is basically a digital light projector, which is also known as a DMD, digital micromirror device, which is actually used by scanning and rotating an array of very small mirrors so that an image can get formulated. And the idea is, if there is a CAD package which can section a particular geometry, the section by section manufacturing can be done by opening and closing the different layers on using that DMD technology or digital light projector technology. Only thing, it's very expensive because you have to have a very good optics, precise optics to avoid or to basically beat the diffraction limitations in such systems, and it basically is again used to sort of cure the liquid curable photopolymer resins like photoresists, and the same manner as it has been done by stereolithography earlier. Instead of a laser at one shot go, this process is much faster actually than the SLA process, the stereolithography process. You can actually have a structure created. These are some typical structures created by the DLP 3D printing. The other technology that is widely used is again this laminated object manufacturing, where there is a laminar sheet which is made up of some kind of paper or plastic or composites or metal ceramics, and what basically this technology does is that in this case the sheet is adhered to the substrate with a heated roller, and there is a laser which traces the desired dimensions of the prototype and cuts it off. Okay, so the laser cross hatches non-part areas to facilitate the waste removal and basically bonds the part areas to the lower already deposited part which was there from a previous roll, and so roll by roll you can create such layers by not changing the position and aligning the different layers, so that you can have the cut parts welded together by laser, and so there is a layer by layer build up of the structures this way. But this is little bit complex process and relatively the FDM happens to be a much wider applied to parts manufacturing through 3D printing, and therefore we have decided that we will probably try to show some of the real applications of this FDM Titan, and feel free to watch the video for this, which is available in the next lecture. So with this I would like to close here for the whole manufacturing technology process 2 domain. We have been able to cover so far advanced manufacturing processes, particularly processes related to small systems like MEMS systems, and we have seen how you can manufacture on silicon, you can manufacture on alternate materials like polymers, you can also manufacture over glasses or ceramics or composites using non-conventional techniques, and then we have done some mechanistic modeling and some details regarding how metal forming can be carried out, and we have classified different metal forming processes, and then finally ended with a small nice introduction on the additive manufacturing. So this is going to be the end of this particular course. I wish you all the best for your quiz and assignments and examinations. If you have any questions, feel free to drop emails to us through the portal, and we'll be very happy to answer some of these questions. The other issue is that the last assignment is going to be due as per the announcements that have been made on the portal, and we are going to be evaluating you on the basis of the assignments and the final examination. So thank you for being patient in listening to all this deliberations regarding this course, and I wish you all the best for your exams. Thank you. Thanks.